Okay, so we're now done with the getting both the discrete and continuous charge, the potential of continuous charge distributions. Let us now relate them, the potential with the electric field. Very important because you see the difference between the formula for the potential and formula for the field, the integral forms. Certainly, the ones for potential are easier uh, to solve simply because there's no square and simply because the potential is a scalar quantity. Yes. We remember this lesson before. We have F is equal to Q times the electric field. So we know the relation between them, and we could do the same thing vice versa. E equals F over Q. So it's fairly straightforward to go back and forth with this thing. Now, we also have this thing, the relation between the potential energy and the potential. So U is equal to QV and vice versa, V is equal to U over Q. Now, let's make the bridge between these two things. It turns out that it can be defined using this formula, this integral. So the potential difference is equal to the negative of the integral EDS. You should also note the similarity of this form to that of the work. And so we have view. I'm introducing it. Might not have been discussed during class. So equals negative of FDS. Actually, this is strictly FDS. Okay, let's not put the negative sign first. It's actually work. So it's the work applied so you should know the basic formula for work. So you could do the same thing here. So for the potential energy, it becomes negative of the electric force. That's for the electric potential energy. So you would see the same thing here. We see it here. So V, we should make it delta U as well. Negative EDS. So along a certain path. So we will apply that here in this example. So this is relatively simple. So we need to find the potential given this plot. So this is just the electric field along x-axis. And we need to find and graph Vx. And we have to assume the following values. So let's check some of the values here. So at x equals 1 meter, it matches here. So 1000 volts per meter. And we check the 2 here, also matching 1000. So x equals 0, x equals 0, x equals 1 meter, 1000 volt per meter, and then x equals 2 meter. So we clearly see the pattern here. So we could actually write a formula for this one. So Ex is equal to 1000 volt per meter x to okay, to make it even more correct mathematically, we add a square here because the x is in meters, so we multiply them, we get volt per meter. So this is the formula we have, and then we're gonna apply it to the formula. So delta V delta V is equal to negative Ex times dx, and then uh, 0 to x. So we'll make it 0 to x. So we already have the x. Oh, sorry. I forgot to. We substitute the formula that we have. So this is equal negative x0. Let's see if we have space. Okay, we have space there. 1000 v over m squared x dx. So we put the constant outside, negative 1000, and then x dx. So this is pretty simple integral that we have here. So let's go straight to uh, getting it. So this is just x squared over 2, x to 0. So we substitute the 0 here. We get 0. Correct. So we only have one term here. So it's negative 500v over m squared x squared. So we actually have v here. So we don't need to reimpose 0 equals 0. It works as well. We could try plotting that. It's an x squared. So when we plot this thing, it's a negative. It's a negative result. I can't get it straight. So it's a parabolic function. So v and x. So that's how it looks like. Okay, so we continue with our somewhat more formulas. So we have this thing is the electric field. We apply the formula. We actually impose the potential at infinity here. This is a common convention. It's not always the case because we had an example where the potential is 0 at x equals 0. So alternatively, we could impose it at value v equals at v at x equals infinity, approaching infinity. So in this case, we set at 0. So this is actually a common option uh, in the potential. And this is actually a hidden assumption on the previous section, getting the integral of the line of charge. So at infinity, the potential is equal to 0. For the potential of the point charge is equal to this one. So it's not hard to understand how we get this form from this integral. Okay, let's try it here again. So electric field inside a capacitor. Capacitor here is defined as having as actually a pair of a positive and negatively charged objects. So let's say we have the positive side here and we have the negative side here. So the electric field is here, directed to this direction. Okay, makes sense. Now let's check the electric field inside the capacitor. It's bound to be this form. Find the electric potential inside the capacitor. Let V equals 0 volts at the negative plate. Oh, okay. We could set it here. So we have x equals 0, x equals x. This is just a sloppy way of saying uh, set distance. Okay. We don't sloppy way of saying we don't want to change the variable. So anyway, we have it here. So at v as v equals 0 volt at x equals x. Let's try to solve it again. equals negative E. So let's impose the condition Ex dx. So we are given the electric field Q over E naught A. So let's not oh yeah, that's correct. That's correct. We'll put it that way. Q naught Q over E naught A dx equals, well, these are constants, so we just put them outside dx. Next is we're gonna do something here. We see the negative. Okay, so let's get the integral form. So it's x from 0 to x. Of course, we get the 0 here, so negative qx over E naught A. So this is the potential. Um, we'll have to impose a condition for the negative axis here. 0 volts. Okay. So let's try that. This is a delta V here. So let's do some sloppy math here. Uh, what can we change here? Oh, okay. Maybe we could do something here. Before around at this portion. Oh, okay. I remember. I'm forgetting something. I remember now. Okay. Uh, let me check this form again. Okay. Yeah. Yeah, yeah. Okay. Let's do it here first. So let's not impose this. Let's not impose a bounds first. So Q E naught A X plus C. I keep forgetting this. Uh, so this is the Vx minus V naught. So here what I did is to expand this thing Vx x equals 0. So it's negative x plus C. So it says here at no, let's erase this one. Since we're having the delta C at this point, so let's make it V again. So what it says here is at V x equals x. So this is where the sorry at x equals x, V equals 0. So it's where the negative charge is located. So 0 equals negative q e naught ax plus c. So for this to be true, c should be equal to positive q over e naught ax. So they will cancel out. Okay. And of course, the electric potential would have a value as along x equals 0. So, okay, I don't know what to do. We'll consider this, we'll define this x as d. So we got too sloppy here. So at x equals d, so we substitute it here, here. Okay, everything makes sense. So let's put it back to the formula. So it's equal to, no, v is equal to q over epsilon not ax plus q. So we have q over epsilon not a d minus x. So this is the answer. Now take note, this is for the case of positive and then negative. It's easy to see if we actually had set it where this is 0. Now in the case where we set negative here, 0 and then positive, so the form would be equal to q over epsilon naught a x. So the presence of t here is like where we want to set v is 0 at negative plate. So that's how it's done. So we have any other examples here? Okay, we actually had here the formula is from E to V. E to V such from variable to potential. Now we want to do the vice versa here. So we're defining it at this form. So we get the derivative of the the potential. So along a certain path. So that's why it says ds. So we could apply it in a simple example like this one. So this is the potential of a point charge and we get it along dr. So it's just a radial distances, just the straightforward distance from the center of the point charge. And we get the following electric field, which is a very familiar form. If we have to do a more general form, like the truly three-dimensional form, is actually it's actually E equals negative like this one. So this is called gradient. So what happens is in the gradient, it converts a scalar field to a vector field. So you probably learned that in 55 if you still have that. But for now, we're going to use this one. So we impose a direction. So we're certainly getting the component along that given direction. So we will try it here. So we found the on-axis potential to be this one. So we're already given the example. Find the on-axis electric field. So it's just along Z. So electric field Z is equal to negative dV over dZ. So I think we still have some space here. We'll copy that. D negative D over dZ 4 pi epsilon naught Q over z squared plus r squared. So we put everything outside the constants q over 4 pi epsilon naught. Yeah, that's right. And then we d over dz. We're gonna rewrite this one to make it clear. So it's z squared plus r squared. Now the squared means it's 1/2. And then q over 4 pi epsilon naught. So what we have here is a form of a power rule. Where it says half, the power is in halves, so it's 1/2. And since it's in denominator, it's negative 1/2. So we apply the integral, the differential. Um, you get the derivatives. It's equal to 1 over c squared plus r squared, 3/2, and then times 2z plus 2z, since r squared is a constant. So it will oh, okay, so we already have the answer here. So this is the electric field. I can seem to get it right. Anyway, that's the answer. Finally have this electric potential. The graph of the electric potential in a region. Graph of we just have to draw. So again, it's just the slope. So you should clear that. It should be clear to us that it's essentially slope of the plots. So here it's positive 10 to 10. So let's make it 10. Then okay. Then and then it's so something like this. So this is 1, this is 4. I think this is 20, and let's make this 5, negative 5.